Welcome to another video on VLSI design. In this video, we'll try to understand the relationship between the source, gate and drain voltages that is applied for the MOSFET. In this structure that we have shown here, this is the three-dimensional structure of the MOSFET. As you can see here, this is the N-type MOSFET, this is an NMOS. Because the body is of P-type and diffusions are of N plus diffusions. This diffusion N plus can be interpreted as source region, and this N plus another N plus region we can interpret as a drain region, and in between the source and drain regions there is a gate region that is shown here, and the terminals are extracted from these four regions. In fact, one is the bulk of the MOSFET at the bottom, what you see, and later we have a source region. The terminal which is extracted is source terminal. From the gate region, the terminal extracted is gate terminal, and the terminal that is extracted from the drain region, this is it is a drain region in a three-dimensional view. So this is the drain terminal here. Now let us try to understand the different voltages that is applied to the MOSFET for proper working. There are three voltages which are very important to be considered to understand the operation of the MOSFET. What are those three voltages? Number one is gate source voltage, the voltage applied between the gate and source, that is labeled as VGS. So we have a VGS. So VGS is nothing but the voltage applied between gate and source. Voltage applied between gate and source. Several DC voltages, so therefore that is the VGS, the voltage applied between the gate and the source terminal. And the next voltage is going to be the voltage applied between the drain and source, which we can call as VDS. So VDS is the voltage applied between drain terminal and source terminal. Okay, and generally the MOSFET bulk terminal is grounded. Okay, so bulk terminal we ground, and we always short circuit the source and the bulk terminal. Okay, so we can show here a short circuit between the source and the bulk terminal. Let us connect here the short circuit. There is a short circuit always between the source and the bulk. Therefore, the voltages that is applied between the gate and source, which we called VGS, is also applied between the gate and the bulk. Similarly, the voltage that is applied between the drain and source, which we have labeled as VDS, so this is also a voltage applied between the drain and the body. Though it is applied to the source, since source and the bulk terminal are short circuited, therefore the voltage applied to gate and source is taken as voltage applied between gate and bulk. Similarly, the voltage applied between the drain and source is also considered as voltage applied between drain and the body or bulk. Okay, so with this, let us now try to arrive at the different voltages, especially the voltage which is between the gate and drain. The voltage that exists between the drain and gate, between these two terminals, can be called as VGD. So this is a voltage that is applied, or that exists between the gate and drain. Therefore, so understanding that these three voltages plays very important role: the gate source voltage, the drain source voltage, and the voltage between gate and drain. Now let us try to derive the relationship between VGS, VDS and VGD. Okay, that will follow in the subsequent. Let us now try to derive to derive the relationship between or relationship among the three voltages that is widely used in MOSFET. The three voltages, namely VGS, VDS and VGD. Okay, let us derive the relationship between all these three voltages. Okay. Okay. All right. Let's first write the equation for VGS. We know that what we know. VGS, gate source voltage, is nothing but it is a difference of voltage applied to the gate terminal minus source terminal. VG minus VS. VGS can be written as VG minus VS. So these are the voltages with that exist at the gate with reference to ground. Similarly, the voltage that exists at the source with reference to ground. Okay. So now this can be modified like this. This can be written equation. This equation can be rewritten as VS equals. So I'll transfer this VGS to the right hand side. So therefore, this VG minus VGS. Okay, so let us call this as equation 1. The alternate equation is VGD. Let us write similar way the equation VGD. So VGD can be written as VG minus VD. Once again, this VD can be taken to the left hand side. Sorry. The VD can be taken to the left hand side. VD equals VG minus VGD. Let us call this as equation 2. Similarly, let us write for VDS. So we know that VDS equals VD minus VS. Now we can substitute equation 1 and 2 in this equation. Let us call this as equation 3. Using equation 1 and 2 in 3, using equations 1 and 2 in 3, we get so VDS equals VD we have from equation 2, that can be written as VG minus VGD, and this minus is as it is. VS is from equation 1, which is minus VG. Minus of this minus becomes plus, which is VGS. Now you can see this VG can be cancelled. So therefore this can be written as, by moving VGS as a first term, this VDS can be written as VGS minus VGD. So this is the relationship between VDS, VGS and VGD. So this is, let us call this as equation 4. This equation is very important in understanding the operation of the MOSFET. So from MOSFET theory, we can write MOSFET working principle. So VGD will decide what region the MOSFET is operating. And in fact, the VGS is also important. So all these three voltages decides the operation of the MOSFET. In the upcoming class, we will discuss how the role of VDS, VGS, and VGD plays a substantial role in understanding the operation of the MOSFET. So that's all about today's video, and the next video will go for detailed operation of the MOSFET transistor. Thank you one and all for watching this.